pressure, volume, and Boyles Law. So we need to convert the following pressure measurements into the requested unit. What you need to know is on the back of your periodic table, in like the bottom right hand corner, it has a column that says defined or exact values or quantities, sorry. And within there, the last three are what we're going to use here. So it says 1 atmosphere is equal to 101.325 kPa. Now, these are two units of measurement for pressure. So we can measure pressure in a variety of ways, and we just have a few different conversions. So 1 atmosphere is 101.325 kPa or kilopascals. And 1 atmosphere is also equal to 760 millimeters of mercury. Millimeters of mercury was one of the first units of pressure. They made something that looked like a thermometer, and every time the mercury rise or fall by 1 millimeter, that would be a change in pressure. So these kind of look equivalent. So we could also say that bringing these two together, that 1 atmosphere is equal to 101.325 kPa, which is also equal to 760 millimeters of mercury, just because they both equal 1 atmosphere. The last one, is 1 bar is equal to 100 kPa. And because this kPa value isn't identical to this one, I can't make it equal in here. We'll use these and get some practice. So we're going to use unit conversion to convert between units of pressure. So if we have 593 millimeters of mercury and we want to convert it into atmospheres, we need to start with our given value. There is a video on unit conversion in our Science 10 review if you want to go back and take a look at it. So to cancel, I'm going to multiply by a fraction, and in the bottom of the fraction needs to be the units I need to cancel. So millimeters of mercury are what I'm going to try and cancel, and we're looking to convert to atmospheres. From here, we need to decide which conversion factor has both of these units in it. Well, atmospheres and millimeters of mercury are equal here. So I'm going to take that conversion factor. I know that 1 atmosphere is equal to 760 millimeters of mercury. Because millimeters of mercury are on the top and the bottom of a fraction, the units cancel, and the only unit left is atmospheres, which is what we wanted our answer in. So multiplying 593 by 1 and dividing by 760, we get 0.780 atmospheres. Now, because there were 3 significant figures in our measured value, there need to be 3 significant digits in our final answer. Remember, this 0 does not count as a significant digit. We have 1, 2, 3. All right, trying the next one. 1.42 atmospheres. We need to cancel atmospheres and convert to kPa. We're going to use our first conversion here. 1 atmosphere is equal to 101.325 kPa. Now it says on your periodic table, use 101. Just always use the exact values. You're going to get a more accurate answer. Atmospheres cancel. We multiply 1.42 by 101.325 and we get 144 kPa. Again, 3 significant figures. 4.903 kPa into millimeters of mercury. Now there's 2 ways you can do this one. So I'll go with my original here. So I'm going to get kPa on the bottom, and we need millimeters of mercury on the top. So these 2 conversions here aren't equal. We don't see that 101.325 kPa is equal to 760. However, when we put these 2 together, based on the fact that they both equal 1 atmosphere, we can see that 101.325 kPa is also equal to 760 millimeters of mercury. So I can use that to finish this up, cancel kPa, and we get 36.78 millimeters of mercury. This time we had 4 significant figures. Now, if you don't like that, if you're like, I don't actually understand what you've done here, don't worry. I'm going to go kind of the long way, if you will, but using both conversion factors. So if you're looking up here and thinking, I don't want to do this, I can convert kPa into atmospheres, or I can convert kPa into bar. If I convert into bar, there's nowhere else for me to go. I'm like stuck at bar. So I'm going to go kPa to atmospheres, and then atmospheres can take me to millimeters of mercury. So I'll just write this out here, and then I'm going to erase it. So 3 kPa, and we decided we were going to go from kPa to atmospheres. And so there's 1 atmosphere per 101.325 kPa, and the units of kPa cancel. Then we need to still cancel atmospheres. This isn't the unit we wanted. We were looking for millimeters of mercury. So we're going to go from millimeters of mercury, atmospheres to millimeters of mercury. 1 atmosphere is 760 millimeters of mercury. And the unit of atmospheres cancels. The only thing I'm left with is millimeters of mercury. You'll notice that we're going to multiply 4.903 by 760 and still just divide by 101.325, which is what we did up here. So mathematically, they are not different. They just look different because we've added these ones in here. Again, in the end, should be the exact same thing. All right, let's do the next one. 1.6841 bar into kPa. Well, bars can be converted directly into kPa. So 100 kPa is 1 bar. We're just multiplying by 100 here, it looks like. So 168.41 kPa should be our final answer. And again, there's 5 significant figures here. Last one, we have 4.327 bar. And we need to convert to millimeters of mercury. Now, the only thing I can convert bar to is kPa first. And then I can use kPa to convert to millimeters of mercury. And I'm going to use this direct conversion without having to go to atmospheres in between. So I'm going to go and convert bars into kPa. So 100 kPa per 1 bar, and the unit of bar cancels. From there, we're going to convert to kPa into millimeters of mercury. Again, you could have, at this step, gone from kPa to atmospheres using this conversion, and then atmospheres to millimeters of mercury using this conversion. Up to you. So there are 760 millimeters of mercury and 101.325 kPa. Units of kPa cancel. Our final answer should have 4 significant figures. We multiply all the way across the top and divide by everything across the bottom. So in this case, we should get 3,246 millimeters of mercury. So get comfortable with converting between units of pressure because some questions will require it of us. Boyles Law says that as the pressure on a gas increases, the volume of the gas decreases proportionally, provided that the temperature and chemical amount, which is the number of moles of gas, remains constant. So I'm not adding any gas to it, and I am not heating or cooling it. This relationship between pressure and volume is said to be inversely proportional because as the pressure increases, the volume decreases. So because these are opposite arrows, this is inversely proportional. All right. A formula for this is that P1 V1, or sometimes we see P initial V initial, is equal to P2 V2 or P final V final. It doesn't matter whether you use I and F or 1 and 2. They mean the same thing. The only thing is that the units of P1 and P2 have to be the same. So this is where our conversions may come in handy. So if P1 is in kPa, so does P2 must be in kPa as well. V1 and V2 must also have the same units. So if we're measuring V1 in milliliters, V2 must also be measured in milliliters. So just making sure that whatever you put in for pressures or volumes have the same units. STP and SATP are just standard conditions. So to measure, states or specific properties of everything, we've defined two specific conditions so that scientists everywhere could replicate the same experiment without having to get really fancy, basically. These are actually listed in your defined or exact quantities, so just above where we found those unit conversions. You don't need to memorize them. STP stands for standard temperature and pressure. This is at 101.325 kPa, or 1 atmosphere, and 0 degrees Celsius, so 273.15 Kelvin. 0 degrees Celsius is kind of cold, and if you're doing this in a lab, you have to cool everything down. So STP is kind of tricky. It requires more work to get to those conditions in a lab. We also have SATP, so standard ambient temperature and pressure, or standard atmospheric. Sometimes they talk about it, temperature and pressure. And so we're going to get 100 kPa and 25 degrees Celsius. So a lot more reasonable in terms of temperature and much easier to get to in our lab. Again, these are on the back of your periodic table. You do not need to memorize them. So a few examples. A weather balloon with a volume of 2,000 liters at SATP rises to a height of 1,000 meters where the atmospheric pressure is measured to be 60.8 kPa. Assuming there is no change in temperature, what is the final volume of the weather balloon? So we are going to use, obviously, our Boyles Law here. What we're going to start with is writing out what we know. I like to just make a little list. And then I just note here that temperature was constant. Okay, because there is no change in temperature. So I know that I'm using P1 V1 equals P2 V2. Let's just fill in what we know. Again, P1 and V1 are our initial conditions, or how things start. So the weather balloon has a volume of 2,000 liters. So that is our initial volume. And we are looking for the final volume. So we don't know V2. It's our question mark here. Our initial pressure isn't actually listed as a number here. However, they say that they are at SATP conditions. SATP conditions are 25 degrees Celsius and 100 kPa. So because I don't care about temperature is constant, I don't need this piece of information. I simply need to write down my pressure. It's going to go to a height of 1,000 meters, which is not important information. Height isn't required here. And the pressure is 60.8 kPa. So we can see here that both of our pressures are the same unit, and our unit for V1 is liters. Therefore, our unit for our final answer will also be in liters, just because they naturally will get the same. All right, looking at our formula, P1 V1 equals P2 V2. We are solving for V2 here. You have two options. You can sub in your numbers and then rearrange, or you can rearrange and then sub in. It does not matter to me what you do first. So I'll show rearranging first here and then subbing in. So if we want to get V2 by itself, I need to divide both sides by P2. P2 cancels here, so I get V2 is equal to P1 V1 all over P2. Let's put in our numbers. 100 kPa times our 2,000 liters divided by 60.8 kPa, and that should be our final answer. Notice that the units of kPa cancel here, and the only unit I'm left with is liters. So that's how we get liters for our final unit of V2. 100 times 2,000 divided by 60.8 is 3,289.47 liters. Oopsie, 47 is what I just said. Now, that's a lot of numbers. And is that how I want to report my answer? Not really. We need to use significant digits. So in our question here, we have a few different numbers. Our measured quantities here were our 2,000 liters, so that is 4 significant figures. We didn't use 1,000 meters, so it's not important. And our 60.8 had 3 significant figures. We didn't consider SATP because it wasn't a measured quantity in our experiment values here. So because this is multiplication and division, we're going to go with the lowest number of significant digits, which is 3. So my final answer should be reported to 3 significant figures. I need to use scientific notation to do that. So 3.29 times 10 to the 3 liters should be my final answer. Some of us may convert to kiloliters. To convert to kiloliters, you'll take your initial answer, 289 liters, and we know that there are 1,000 liters in 1 kiloliter. So dividing by 1,000, I get 3.289 kiloliters. So rounding that to 3 significant figures, we get 3.29 kiloliters. It doesn't matter what you write. Lots of us will write this. Some of us will write this. You are both correct if I haven't specified a unit. A 2.5 liter sample of gas is trapped in a trapped at 100 kilopascals in a cylinder with a movable piston. If the pressure rises to 3.35 atmospheres while the temperature is kept constant, what is the volume of the sample in a cylinder? So let's list our information here. So we were given an initial volume of the cylinder of 2.5 liters and an initial pressure, so 100 kPa. We were given a pressure after, which was 3.35 atmospheres. The temperature is constant, and the volume is what we're looking for in the end. If you noticed, we have units of kilopascals and atmospheres. We need to convert one of these to the other unit. So it doesn't matter which way you convert. You can convert kilopascals to atmospheres, or you can convert atmospheres to kPa, or you could convert them both to millimeters of mercury. It really doesn't matter. I am going to convert atmospheres to kilopascals before we get started. So showing our work, we started with 3.35 atmospheres. So we need to cancel the unit of atmospheres and convert to kilopascals. Using our conversion sheet, there are 101.325 kilopascals in 1 atmosphere. Atmospheres units cancel. The only unit left, is kPa. So, my final answer is 339.4 kPa. Now, technically, this was 3 significant digits, so I should round this to 3 significant digits. Because it's not my final answer, it's not what the question was asking, I don't have to. So typically for interim calculations, so ones that help you get to your final answer but aren't actually your final answer, you might want to consider keeping 1 extra significant digit. At least keep the number of significant digits that you're supposed to. So don't round this to 2 significant digits. Okay, continuing on to our formula, P1V1 equals P2V2. This time I'm going to sub in and then rearrange. So we had 100 kPa and V1 was 2.5 liters. P2 was 339.4 kPa. And we're looking for V2. So divide both sides by 339.4 kPa. And units of kPa cancel here. V2 we are left with 0.73651 liters. I'm going to keep some extra significant digits here. Looking at our question, we originally had 2 significant figures in this number, 3 significant figures here, and 3 here. So because we used only multiplication and division in this case, we're going to be using 2 significant digits, the lowest number. So my answer should be 0.7, geez Louise, 0.74. 0.74 liters. Another example here, a flexible container holds 4 liters of air at 22 degrees Celsius. If the temperature of the air remains constant, so temperature doesn't change, what will be the volume of the air if the pressure doubles? So you can see that we were given a little bit of information. Let's list out what we know, V1, P1, V2, P2. So V1 was 4 liters. And the temperature is 22 degrees Celsius. It says if it remains constant, so T is constant. What will happen to the air if the pressure doubles? We weren't given an initial pressure. So what we can do is we can pick any number, and then we're just going to apply that ratio. So whether it's doubled or a half or whatever it is, you can literally pick any number. I'm going to pick 1 because that's just an easy number to work with. And I'm going to put a unit of kPa in there because I know that kPa is a proper unit of pressure. So if it's doubled, double 1 is 2. If you put 75 and 150, you're still going to get the exact same answer as me in the end. So we're looking for V2 here. Units of pressure are the same because I picked them. So we just need to sub into our formula here. So V2 is equal to P1 V1 over P2. We've done a lot of solving for V2 this time. 4 liters times whatever pressure you have for your initial divided by whatever pressure you have for your final, that was twice as much. In the end, I'm going to get 2 liters. If it asks by what factor did this change, we need to decide if this was a multiply or divide to get from 4 to 2. Technically, I guess it could be both. Just depends what you're multiplying by. So it's getting smaller, so I would say it was divided. And I divided by 2. So therefore, it decreased by a factor of 2. That's not exactly what this question asked, but there are some that ask that. So if my number had gotten to 16, let's say, that had increased, that was a multiplication by 4. So this increased by a factor of 4. So a little experiment that shows Boyle's Law is a balloon in a vacuum chamber. So this balloon wasn't really inflated very much, and this is when the chamber hasn't, or the vacuum hasn't been turned on. We've just like gently put the little bell jar over top. As we start to suck out the air in the vacuum, so remember we're removing air particles from around this, we can see that the balloon gets bigger. So why is this happening? We're going to use kinetic molecular theory to explain this. So initially, the internal pressure on the balloon and the external pressure, what's in the vacuum chamber, are the same. There's an equal number of collisions inside and outside. So initially, if this was our jar and our balloon, the number of collisions outside, which remember initially was like atmospheric pressure, is equal to the number of collisions inside the balloon. Okay, so these are molecules bouncing off in each case. So they're equal numbers, therefore the balloon doesn't expand or contract. When the external pressure is decreased, so when we remove the pressure from around the balloon, the volume of the balloon will increase. Okay, this is because, another little drawing here. So if we could get an instantaneous representation, I've removed collisions from outside the balloon, but the pressure inside the balloon is still the same. So what happens is because there are more collisions inside or a higher pressure, this balloon will start to expand. As the balloon expands, the particles have more room and collide less. So let's draw that. So my balloon expands a little bit and it has a few, like one less collision. It expands some more. You're going to get the idea here. it expands until the number of collisions inside the balloon matches the number of collisions outside. So this only works with a flexible container, aka a balloon or a piston. And they will always look to be equal at the beginning of the experiment and the end of the experiment. As it starts to change, the number of collisions were uneven. Remember, there were fewer outside than there were inside, and that's what caused it to grow. So we'll talk about both of those pieces when we're asked about kinetic molecular theory. You're going to make a statement about initially it's not changing because everything's equal. And then as I sucked the air out of the bell jar, the number of collisions outside was less than the collisions inside. So this pressure allowed the balloon to expand. The balloon will continue to expand until those number of collisions inside and outside are equal again. Some practice in your textbook here to help you get an understanding of Boyle's Law.